Hello class, this is Mrs. Ayodeji with today's video on 11.4 rational functions. As you're watching the video, please feel free to pause, rewind, or repeat as often as you need to get a clear understanding of what is occurring in the video. Don't forget to write down important vocabulary, formulas, equations, and any important information in your notes. At the conclusion of watching the video, write a brief summary of what occurred in the video and submit that summary as well as a thought-provoking question via the online quiz the night before class. All right, let's begin. So today we're going to talk about rational functions. And although you guys have seen rational functions before, we have not done an in-depth study on rational functions. And a lot of your questions are talking about when are we going to use it in real life? Well, I'm going to start off the discussion of rational functions with a real life example. So let's talk about the average cost of producing a therapeutic drug. So let's say that we have a model C that describes the cost in dollars of making Q grams of a drug. And this is the cost model. Okay, and if you guys remember when we're dealing with cost, there's two types of costs, fixed costs and variable costs. So the fixed cost is the cost that doesn't change in spite of the amount of the quantity. And so in this case, the fixed cost is $2.5 million, and that can go into research, staff, whatever the cost is to come up with the drug. And then we have a variable cost, which varies depending on the quantity. And in this case, we have a cost of $2,000 to produce 1 gram of the drug. So what we want to look at now is the actual average cost, including the variable cost and the fixed cost. So that's average cost per gram. So right now, if I want to figure out the total cost for 10 grams, I plug 10 in for my value and I get out $2.52 million. But how much does that cost per 1 gram of the drug? And that average cost, well, I divide it by 10 grams and I get $252,000 per gram of drug. And that means it's quite expensive to produce just to produce 10 grams of drug. You actually need to produce more than 10 grams. So let's say to make it cost efficient. So let's figure out the cost of producing 10,000 grams. When I produce 10,000 grams, the total cost is over $22.5 million. But when I divide that by 10,000, I get an average cost of $2,520 per gram of the drug. So then, of course, the question is, well, really, what's the lowest average cost per gram of the drug can you get? And in order to do that, we're going to define a different function called A of Q, and that's basically divided by the same thing we were doing before, total cost divided by the number or the quantity of grams. And we end up, if I use a table of values and trying 10,000, 50,000, 100,000, 500,000, I end up with average cost being around $2,000. And so the question is, will it ever go below $2,000? Well, if we take a look at the graph of the function, we see that the graph does not go below $2,000. And in fact, we have a horizontal asymptote at y equals 2,000. We also have a vertical asymptote at x equals 0 because the cost would be ridiculously large to produce a very small amount of the drug. Okay? So back to our original topic, what is a rational function? Well, that was the average cost function was actually an example of a rational function. And by definition, if function r can be written as a ratio, in other words, dividing two polynomial functions p of x and q of x, then we say that r is called a rational function. And we assume in all cases for rational function that the denominator function q of x is not the constant polynomial function. Now, the numerator polynomial function can be a constant function. It can actually also be zero function, but it would be a very trivial, simple case of a rational function. So in other words, every rational function is the ratio or the quotient of dividing two polynomial functions, as long as the polynomial function in the denominator is not the zero function. So just like we dealt with long-run behavior of polynomial functions, let's look at the long-run behavior of rational functions. And here's a very important point. In the long run, every rational function behaves like a power function, just like in the long run, every polynomial function behaves like a power function. And to do that, we're going to take a look at this example. This is a rational function because it is the ratio or quotient of two polynomial functions, as we can see, and the denominator function is not the zero function. And if you recall, since the numerator function is a degree 4 polynomial function with the leading term of 6x to the 4th, and the denominator function is a polynomial function with the lead term being 2x squared, then we have at the long run behavior, the numerator function looks like 6x to the 4th, and the denominator function looks like 2x squared. And that's when x is really, really big, and that's when x is really, really small. And when I divide these two functions by one another, I get 3x to the second power. So essentially, I can describe the long run behavior using the limit in my description. The limit as x goes to positive or negative infinity of this f of x function is going to be the same as the limit as x goes to positive infinity to this 3x squared function. And we know that is positive infinity. Let's take a look at the graph. So as you can see, this is the rational function that we talked about. And it looks very weird and different from functions that we are normally used to. So when we're trying to graph this, like we talked about the end behavior, we're not really concerned right now about the middle, but we're really concerned about what's going on at the end. And as you can see, like we talked about earlier, it looks very similar to the power function of 3x squared at the ends, okay? So this is very important for you to understand, and this example describes this. In general, if r is any rational function, then for very large values of x, this rational function r with the polynomial in the numerator and polynomial in the denominator, in this case, the polynomial in the numerator has a leading term of a n sub n x to the n, and the denominator of b m x to the m. Well, that means that in the long run, it's going to look very much like this power term. Oops. And this power term looks very much like another way of writing this power term is this right here. So you basically divide the leading coefficients of the numerator and the denominator polynomial, and then subtract the degrees or the powers of the numerator and denominator polynomial, like we did in this example up here. Okay? All right, moving on. Another way to say is for x of very large enough magnitude, either positive or negative, the graph of the rational function looks like the graph of a power function. This is basically a summary. The long run is given by the leading term of p divided by the leading term of q, and this is a way to describe the long run behavior of the rational function. And interestingly enough, not only will this describe the long run behavior of the rational function, but it also describes what the horizontal asymptote is of the rational function. So let's take a look at some examples of rational functions and see if we can describe or predict the long run behavior. Here's an example of a rational function. The polynomials are linear functions in the numerator and the denominator. And if x is a large positive number, then the rational function is going to be some really big number plus 3 divided by some really big number plus 2, which approximately is equal to some big number divided by an approximately very similar big number, only differing by one value. So that means it's going to be equal to 1 for very large positive number values. And let's take a look at the picture right quick. So here's the example of the function for x being very large positive values. And as you can see, it never crosses the horizontal line y equals 1, not only on the positive side, but also on the negative side. Here's another example, and here we have a rational function with a linear function in the numerator and a quadratic function in the denominator to make up the rational function. And so, like what we said in the previous thing, we take the leading term of the numerator and divide it by the leading term of the denominator, and we end up with 3 over x. And as we all know, I did this wrong color, had to fix the color. Anyway, we end up with 3 divided by x. And so as x gets really, really, really big, then 3 over x goes close to 0, which means that the long run behavior is approaching 0. And let's take a look at the graph and see. Now this is what the graph looks in this case. And I know you're thinking, wow, that looks really weird, especially this middle stuff. But we're not focused on the short run behavior of rational functions. We're focused on the long run behavior. So let's look at the long run. And as you can see, it's approaching 0 for x being very, very large, and it's approaching 0 for x being very large as well too. And the reason why is that if you take a look at the numerator function is actually going to be, for very big numbers, is actually going to be smaller than the denominator function, and that's why you get it being close to 0. So the last topic, what causes asymptotes? Well, if we take a look at our first example, the asymptote was y equals 1, and that was because the numerator polynomial and the denominator polynomial were the same type of polynomial, same degree polynomial. So for very large numbers, it was basically the leading term divided by the denominator term for the denominator, which ended up being close to 1, as you can see, 1x divided by 1x. And that same thing occurred when x was very large in the negative sense. You still had a negative large number divided by approximately the same negative large number, and that's why you ended up being close to 1. In example 2, you had a numerator of a linear function and denominator of a quadratic function, and the quadratic function grows faster than the polynomial function, the linear function. So you had a large number divided by even bigger large number and then for both situations. And that's why the long run behavior looked to be close to have a horizontal asymptote of y equals 0. Okay, that's it. I'll see you in class. Bye-bye.